In this video, we're going to go over reaction rates and rate laws. So what is the rate of a chemical reaction? The rate is the change in concentration divided by the change in time. And oftentimes these brackets just notate concentration. So let's see what this means. Let's say we have a beaker that starts with our reactant A. And over, let's say, 1 second, 3 of those A's turn into our product B. In just the simple reaction, A goes to B. So if we want to find the change in concentration of A, we do final minus initial. So we have 2 A's, and we subtract our 5 A's that we started with, and divide by our time of 1 second. So if we simplify that, we get -3 molecules per second. And that would be our rate for compound A. For compound B, our final would be 3 molecules, and our initial was 0. So for that 1 second time, 3 minus 0 would be 3 molecules per second. For compound B. And this logically makes sense. Since A is our reactant, it should be decreasing, which is where we get the negative sign, whereas B, which is our product that we're forming, is positive. So the rate should be positive since B is increasing. Now, one aspect of a rate is that it should be the same for both of the reactants and for the products. So if we look at our generalized definition that a rate is equal to the change in concentration divided by the change in time, we can see that in this example here, we'll be using 3 H2s for every 1 N2. So our hydrogen should decrease faster than our nitrogen. So therefore the rates would not be the same. So to counter this, when we write our generalized rates, we can write that the rate of the reaction is equal to 1 divided by the coefficient, which in this case is 3 for hydrogen, times the change in concentration of hydrogen divided by the change in time. And that 3 accounts for the hydrogen being used up more rapidly than the nitrogen. And then we also can add a negative sign in front of this since we're decreasing the hydrogen. And then we can set this equal to both our other reactant and for the product by doing the same thing. So for nitrogen, it's our reactant, so it should be negative, and the coefficient is 1, so we put 1 in the denominator. And then we can just write the change in the concentration of nitrogen divided by the change in time. Then for the products, since we're forming the products, we don't need the negative sign. And since the coefficient is 2, we put 2 in the denominator. And then we write the concentration of NH3 divided by the change in time. And since here we're accounting for the coefficients in the reaction, all of these should be the same. So let's look at an example for this. We're given the equation 2N2O goes to 2 nitrogen plus oxygen. So first let's write the rate of the reaction. So the rate of the reaction for N2O, since it's our reactant, it will be negative, and it's 1 over the coefficient. And then we just write change in the concentration of our reactant divided by change in time. And then this is also equal to nitrogen. Since nitrogen is our product, it's positive, and then 1 over the coefficient times change in concentration of nitrogen divided by change in time. And then the same for oxygen. Since our coefficient is 1, we just put 1 in the denominator. To find our average rates, we can just plug in the values from this table. Oh, okay, hold on. Part B gives us a table of times versus the rates for, or versus the concentration of nitrogen, and then asks us to find the average rates for given times. So to find the average rate, we can just apply the equation that we wrote above. So the rate of the reaction is negative 1 over 2 times the change in concentration of N2O divided by the change in time. So let's do from t equals 0 to t equals 5. So that would be equal to negative 1/2 times our final concentration, which is 0.05, minus our initial concentration, which is 0.1, and then divided by the change in time. So the final time is 5 minus 0. And if we plug this into our calculator, it simplifies to 0.005 molarity per second. And this is for t equals 5, t equals 0 to t equals 5. Now let's do the same for t equals 5 to t equals 10. So the rate of the reaction is negative. Oh, and this would be a negative here, since we have the negative from the beginning. So for t equals 5 to t equals 10, the rate of the reaction is equal to negative 1/2 times the final concentration minus the initial, so 0.025 minus 0.05, divided by our change in time, so from 10 to 5. And this simplifies to negative 0.0025 molarity per second. And we can notice here that at the beginning, the rate is larger than as it approaches 10 seconds. Let's do a quick side note about average rate versus instantaneous rate. So if we're looking at our reactant, our concentration should be decreasing as time goes on. So if we're looking at our average rate, let's say from the time of 0 to 5, as we did in the last problem, the average rate is a line between those two times, and we're looking at the slope of this line. Now, if we're looking at the instantaneous rate, let's say at time is equal to 5, rather than the slope between 2 points, we're looking at the slope of the line that is tangent to the plane at that point, or tangent to the line at that point. And these average and instantaneous rates are related to each other. For example, if we looked at the average rate between time 0 and 10, since 5 is the midpoint of 0 and 10, the slopes will be approximately equal to each other. And if we look at the average of the instantaneous rate at the midpoint of 5 and 0, which would be about 2.5, and we look at the instantaneous rate at that point, we can see that the slopes are also similar to each other. So if we said that the rate is the change in concentration over the change in time, rate laws are really answering the question of how does the concentration affect the rate. So for the simple reaction of A going to B, if there is in excess of A and there's plenty of A around, it'll react really fast to form B. Whereas on the other hand, if there's only a little bit of A, it'll react more slowly to form B. A real-life example of this might be a person with a lot of money might spend that money at a more frivolous rate compared to someone who doesn't have as much money. And the amount that the concentration affects the rate, that's what we call our reaction order. And the reaction order is always going to be either 0, 1, or 2. And we have simple equations for each of them. So for a 0 order reaction, the rate is simply equal to K, where K is our rate constant. And that never changes for a given reaction. If the reaction is first order, our equation is rate is equal to K times the concentration of our reactant, which is A in this case, and it's to the first power because the reaction order is 1. And for a second order reaction, the rate is equal to K times A, the concentration of A, to the second power. And so the reaction order with respect to a certain reactant can only go up to 2, but the reaction order for the whole reaction could be higher. So let's look at A plus B goes to C. The rate could, for example, be equal to K times the concentration of A, first order, times the concentration of B, second order. So it's second order with respect to B and first order with respect to A. But the overall reaction order would be 2 plus 1, so it would be 3. So let's do an example of this. For the reaction 2NO plus O2 goes to 2NO2, the reaction is second order for NO and first order for O2. Write the rate law. So our rate law is just the rate is equal to K times our reactants, so NO and O2. And then it is second order with respect to NO, so we put the second power, and first order with respect to O2. So that's all we have to do for the rate law. In part B, when the concentration of NO equals 0.2 molars and the concentration of O2 equals 0.1 molar, the rate is 0.018 molar per second. Calculate K. So here we want to use our rate law and plug in what we already know. So the rate is 0.018 molar per second, and that's equal to K times the concentration of NO squared, which is 0.2 molar, times the concentration of O2 to the first power, which is 0.1 molar. And then we can solve this for K. So K is equal to 0.018 molar per second divided by 0.2 molar squared times 0.1 molar. And if we plug this into our calculator, we should get 4.5. And when we're using rate laws, our units are important. So on the top, we have molar, and then second to the negative first. And then on the bottom, we have 2 molars from the NO and 1 molar from the O2. So that's molarity cubed. And we can simplify these units. 1 minus 3 is negative 2. So molarity to the negative second, seconds to the negative first. And that will give us our units. Now in part C, calculate the reaction rate when the concentration of NO is equal to 0.035 molar and the concentration of O2 is 0.15 molar. So now what we want to solve for is the rate, and we can again plug in what we know. So for K, we just solved K, so we can plug that in. 4.5 molarity to the negative second, seconds to the negative first, times the concentration of O2 squared, 0.035 molar squared, times the concentration of O2, so 0.15 molar to the first. And if we plug this into our calculator, we get that our rate is equal to 0.00083. And then for our units, we have 3 molar minus 2 molar, so molarity to the first, and then seconds to the negative first. So there's our answer for the rate. Now here's another example. So we're asked to determine the rate law and rate constant from experimental data. So whenever we want to find the rate law, we're going to need to know the reaction orders with respect to each of the reactants. So the way that we can solve for that with experimental data is this equation I've written here. So we can take the rates and divide the rate laws by each other for two separate experiments. And what we get if we do that is that the rate constants, these K values, since they're always going to equal each other, will cancel out and equal 1. And then if we plug in our concentrations for ClO2 and for OH- between the two experiments, what we can do is we can find an experiment where one of the concentrations are held constant. So if we look at experiment 1 and experiment 2, the concentrations of OH are both 0.03 molar. So then if we plug that into our equation below for experiments 1 and 2, the OH over OH will equal 1, and 1 to any power will still equal 1, so those will cancel out. So let's plug it in. So we always put the larger rate on top, so it looks like experiment 1 is larger here, and that's just so that we get a whole number instead of a fraction for our final reaction order. So our rate is 0.0248 molar per second for experiment 1, and for the second experiment it is 0.00276. And then our K's cancel out, so we can ignore those. Our concentrations of ClO2 are 0.06 and 0.02 respectively to the m power, and then our concentrations of OH are both 0.03 to the n power. And since 0.03 over 0.03 is 1, that will cancel out because no matter what the exponent is, it will always be equal to 1. So then, if we simplify this in our calculators, we should get 8.99 is equal to 3 to the m power. And we could solve this using logarithms, but the easier way is just to plug in the numbers that it could be. Since we know the reaction order with respect to a variable is always 0, 1, or 2, 3 to the 0 is equal to 1, 3 to the 1 is equal to 3, and 3 squared is equal to 9. And so since 8.99 is approximately equal to 9, we can say that m is equal to 2. So our reaction is second order with respect to ClO2. Then we can do the same thing to solve for OH, but instead of keeping the OH constant, we want to keep ClO2 constant. And it looks like in experiments 2 and 3, the ClO concentration is held the same. So again, we put the larger rate on top, so 0.00276 divided by 0.00828. and then again our K's cancel out. Our concentrations of ClO2 are 0.02, and that's to, well, now we know that m is equal to 2, but it's not relevant because 0.02 over 0.02 is 1, and 1 squared is just 1. And then for our concentrations of OH, we have 0.03 and 0.09. And that's to the n power, which is what we're trying to solve for. And it looks like I put them upside down, but it should still work out the same. So if we plug this into our calculator, we should get 1 over 3, or 0.33 repeating, is equal to 1 over 3 to the n power. And since we know that anything to the first power is itself, 1/3 to the first power is 1/3, so n must be equal to 1. So then with that, we can write out our rate law, since we solved the reaction orders for both reactants. So our rate law then is the rate is equal to K times the concentration of ClO2 to the second power, and the concentration of OH minus to the first power. Now that we determined the rate law, we have to solve for the rate constant, the K value. So to do this, we can just pick any of the experiments. Let's do experiment 2 and plug in everything we know. So the rate is 0.00276 molar per second, and that's equal to K times the concentration of ClO2 squared times the concentration of OH to the first power. And if we plug this into our calculator, we should get that K is equal to 230 molarity to the negative second, seconds to the negative first. Here's another example. You can pause the video to try to solve it on your own. So we're going to solve this similarly to the last problem. First, we're going to try to find two experiments where the concentrations are held constant. So it looks like for I minus in experiments 1 and 2, it's held constant at 0.036 molar. So then we find the larger initial rate, which looks like experiment 2, and put that on the top of our fraction. The K's will cancel out, and then we put the concentration of S2O8 2 minus for experiment 2 on top, and then for experiment 1 on the bottom. And that'll be raised to the m power, which is what we're trying to solve for. And then for I minus, they're held constant at 0.036 molar. And so those will then cancel out. And now we can plug these into our calculator to simplify it. And we get on the left side 3 over 2. And on the right side 3 over 2 to the m power. And since anything raised to the first power is just itself, m must be equal to 1. So our reaction is first order with respect to S2O8 2 minus. Now here's where it gets a little bit more tricky, because there is no experiment where we hold S2O8 2 minus constant. But if we set it up for experiments 2 and 3, we'll see that since we already solved for m, we can still solve for n, since there's only one variable left in the equation. So we put the larger initial rate on top for experiment 3 and experiment 2 on the bottom. And this could also be done with experiments 1 and 2 or experiments 3 and 1, and you'll get the same answer. Then our k's will cancel out, and now we can put concentrations of S2O8. So we have 0.036 on the top and 0.027 on the bottom for experiment 2. And now that we already solved for m, we know that m is equal to 1, so it must be the first power. Then our concentrations of I, we have 0.054 on top and 0.036 on the bottom. And that's raised to the n power, which we're trying to solve for. And so now if we simplify this in our calculator, we get that 2 is equal to 4 over 3 to the first power times 3 over 2 to the n power. So now we can divide by 4 over 3, and since we're dividing by a fraction, that's the same as multiplying by its inverse. So 3 over 4 times 2 is equal to 3 halves to the n power. Then we can simplify that as 6 over 4 is equal to 3 over 2 to the n power. And that can further be simplified to 3 halves is equal to 3 halves to the n power. And we can see that n is also equal to 1. So now that we solved that m is equal to 1 and n is equal to 1 for this equation, we can write our rate law. So the rate is equal to k, the rate constant, times S2O8, 2 minus, to the first power, times I minus, to the first power. And now lastly, we have to solve for our rate constant. And we can pick any of the experiments like before. So this time, let's do experiment 3. So the rate is equal to 7.8 times 10 to the negative 6th molarity per second. And that's equal to K times the concentration of S2O8 2 minus, which is 0.036, times the concentration of I minus, which is 0.054. And then we divide both sides by 0.036 times 0.054. And we see that K is equal to approximately 0.0040 with 2 significant figures. And then the units for that will be molarity to the negative first, seconds to the negative first.